All right, let's take a look at this hot mess of a problem. This is the airplane one. Some people mentioned in class that they had a tough time visualizing what was happening in this problem, so let me kind of draw you a cute little picture without any math involved, and then we'll, kind of actually take a look at the model, okay? So let's just make sure we understand what's happening. It says an airplane is flying at an altitude of 5 miles, okay? All right, so what are we dealing with? We're dealing with a plane. I'm not drawing a plane, sorry. Here's the plane. Okay, and it's traveling, right? It's moving at some speed, which we don't know, and that's what I'm asking you to find is the speed, but we know that it's sort of traveling in this direction, all right? We just don't know the speed at which it's traveling, but it's moving, okay? When the plane is 10 miles past the antenna, all right, so what's happening there? So there's some random radar antenna over here. I guess that's what it looks like. I'm just going to put the word radar, so that way you can't tell me that's not what it is, because now it's labeled, so that's exactly what it is. So he's going to pass over this radar antenna or whatever, and then I want to know when the distance, as this plane is traveling, so as he's moving, right, when the distance between the plane, which would now be over here somewhere, when it's 10 miles, I want to know the speed. All right, when it's 10 miles away, I need to know the speed. That's essentially what we're doing. All right, didn't know the speed. I want to know when at 10 miles, once the plane and the antenna are 10 miles apart, how fast is that plane going? The other piece of information that we need is this right here, this 240 miles per hour. Okay. Now let's think about what that particular rate is representing. Well, what would the distance be from the plane to the radar antenna, right? So the distance would always be measured in a straight line, so it's going to look like this, right? That's the distance between the plane and the radar, all right? So, of course, as you can anticipate, we're going to try to use a triangle, okay? So it looks like this is one of the legs of the triangle. That's 10 miles, okay? We're looking, or we have a rate of change for this distance here. Okay, we have a rate of change. We don't know what that distance is, but we know how it's changing. And we have a fixed height or fixed altitude here. Okay, so it's clearly being modeled by a right triangle, okay, which we can anticipate, or that's something that you can expect. All right, so that's what's happening. Plane's moving, passes over a radar gun. I want to know when it's 10 miles away, what's the distance between, what's the speed when it's 10 miles away from the radar. All right, that's essentially what we're doing. Okay, so let's see if we can clean this up and do an actual model here. Hopefully that was helpful. Okay, so let's do this right triangle. So let's see, we know that this is 5 miles, right? Yep. We know it's traveling in this distance. Okay, we're going to call it x for now, okay? Because it's not 10 miles in the whole problem. I'm asking you to take a snapshot when it's 10 miles, okay? The distance is always changing, but once it hits 10 miles, that's when I want you to basically take the speed, okay? We're taking a speed check right at that 10-mile marker, all right? And then I'm going to have to call this something. I guess I'll call it y. We don't have a length for that line, but we do have a rate for that line, all right? So this is basically how, this is basically how I'm going to model this situation, okay? Hopefully that's all right. So then where would you go from here? Okay, well, now that I've got some variables and I know that I'm dealing with x's and y's and I have my constant altitude, let's see. So this rate here is going to be dy dt. Okay, that's just the change in the distance between the radar gun, which is over here. Let me do, I guess I could do a better picture. This is the radar thing, and then this is the plane. All right, so that's going to be dy dt. That's that changing distance here. 5 was given in the problem, and we know that this is changing, but we're going to take a little snapshot right at 10 miles. Okay, all right, so of course what's going to relate these together is Pythagorean theorem. So I like to just write out whatever equation I'm using first, and then I'm going to plug in anything that I can. I'm going to plug in anything that I can So like it'd be x squared plus, in this case, 5 squared equals to y squared. Okay, now that's the key. All right. Now from here, you just got to differentiate, plug some things in, yada yada, but that really is the calculus piece of the problem, is understanding what is changing, getting a mathematical model, and now we're just going to do some calculations here. All right, so we're going to implicitly differentiate both sides like we're used to, and then we should be good to go. All right, so let's do this side here first. So this will be 2x dx dt plus nothing because it's a constant equals 2y dy dt. Okay. All right, so now we're at the plug-in stage, right? So we're gonna have some values and some rates from the problem or from our calculations, and then some rates we're gonna have to go back and find. All right, so when I look at this, I do have an x, right? I know what the x is because it's 10 miles, right? Even though this was changing throughout the problem, now it's 10 miles. So we're gonna plug in for 10 right there. dx dt. Well, dx dt is what I'm trying to solve for. That's going to represent the speed over time, right? So we're looking for this. We're going to end up solving the equation out for that particular rate. The y value, unfortunately, I don't have, and that's going to be a problem. So we're going to have to calculate that, all right? We're going to use Pythagorean theorem. And then dy dt we have as 240, which we always had, okay? All right, so let's go after the value of y because I do need to plug it into the right side of the equation. So because it's at 10, we know the distance of x. So we're going to do 10 squared plus 5 squared equals to y squared. So y is equal to the square root of 125. All right, so it looks like I pretty much have what I need. So we're going to do the plug-in step here. So it's going to be 2 times 10, that's where we're taking the snapshot. dx dt is just the speed of the plane, that's what we're solving for. 2 times y, we had to calculate that, so we're going to do the square root of 125. And dy dt is the distance, or the rate of the change of the distance between the antenna and the plane, which was 240. That was part of the problem. All right, so now it's just, I guess, divide both sides by 20. Is that right? I think that's right. So, oh God, what's that going to be? So, 480, I guess, for the constants. Root of 125, I think that breaks down. 2 times 10, of course, is 20. All right. So, I mean, that's the answer right there. I just got to slap some units on it. And you can definitely simplify it a little bit. You can definitely give me a decimal, but if you put that and you slap some units on it, it's good to go. All right. So if this was a problem where you had a calculator, you can give me a decimal. If you didn't have a calculator, then leaving it like that's totally fine. Okay. Maybe simplify the 480 over 20. What would that be? 48 to is that 24? I think it's 24. And then the root of 125 won't go away. That will stay. And then the units would be what? It's miles, right? So miles per hour. Okay. All right, not as bad as I think you guys are making it in class. I think the hardest part on this one is really understanding the word problem and how the plane was moving.